In this video, we will explore static members in C++ classes. Static members are class-wide data and functions that are shared by all objects of the class. Let's dive in to understand how they work and how they are useful. Let's first understand what static members are. We will look into static data members and static member functions. Static data members are declared using the keyword static inside a class. They are shared by all objects of the class. Only one copy of a static data member exists no matter how many objects are created. They must be defined outside the class declaration. Static data members exist even when no objects of the class exist. Now let's move on to static member functions. Static member functions can only access static data members or call other static functions. They cannot access non-static members of the class. Static member functions do not have a this pointer. They can be called using the class name without creating any objects. These functions are used for operations that are related to the class as a whole, rather than to a specific instance of the class. Let's look at an example of static data members. Here we have a class called counter. Inside the private section, we declare a static integer variable named count. This is a static data member declaration. We also have a non-static data member called ID. In the public section, we have a constructor for the counter class. Every time an object of counter class is created, the constructor is called, which increments the static count variable and assigns the increment value to the ID for each object. There is also a getter function to return the value of ID. Remember that the static data member must be defined outside the class. The syntax is int counter, count equals 0. Here we are defining the static data member count and initializing it to 0. Let's see how to use the counter class. First, remember that the static member count needs to be defined as int counter, count equals 0. In the main function, we create three objects of the counter class, C1, C2, and C3. When C1 is created, its ID is assigned 1, as the static count variable is increment from 0 to 1. Similarly, when C2 is created, its ID is assigned 2, and when C3 is created, its ID is assigned 3. Each object has its own ID, but all objects share the same static count variable. All counter objects share the same count variable. Each object gets a unique ID based on the shared counter. The static member persists throughout the program's execution. Memory for static data is allocated only once. Static members have class scope, not object scope. Now let's explore static member functions with an example. Here we have a class called mathUtils. Inside the private section, we have a static double variable named pi. In the public section, we have a static member function called getPi, which simply returns the value of pi. We also have another static member function called circleArea, which takes the radius of a circle as input and returns the calculated area using pi times radius squared. Note that static member functions can be called without creating an object of the class. For example, double area equals mathUtils, circleArea 5.0. We can directly call the function using the class name and the scope resolution operator. Also, the static member definition should be outside the class. The syntax is double mathUtils, pi equals 3.141592653589793238846. Now let's see how static members can be used to implement the Singleton pattern. Here we have a class called Singleton. Inside the private section, we have a static member variable called instance, which is a pointer to a Singleton object. We also have a private constructor, which ensures that no objects of the Singleton class can be created directly. In the public section, we have a static method called getInstance. Inside this method, we check if the instance is null. If it is, we create a new Singleton object and assign it to the instance variable. Then we return the instance. The Singleton pattern ensures that a class has only one instance and provides a global access point to that instance. It uses a static member to hold the single instance. The constructor is private to prevent direct instantiation, and the static method controls instance creation. Let's look at the best practices when using static members. Always initialize static data members outside the class. Use static members for data that belongs to the class, not to instances. Consider thread safety when using static members, especially in multi-threaded applications. Avoid using static members as global variables, as this can lead to code that is hard to maintain and debug. From C++17 onwards, you can use inline static for in-class initialization. Here is an example. Class example inline static int value equals 42. Here, the static data member value is declared inline and initialized to 42 inside the class. Let's also see some common use cases for static members. They are used for counters to track the number of instances of a class. They are used for configuration data shared by all instances of a class. They are used in Singleton pattern implementations. They are also used for factory methods that create objects, utility functions that don't need object state, constants that belong to a class, and caching mechanisms shared across instances. Let's quickly summarize what we have learned about C++ static members. Static data members are shared by all objects of a class. Static member functions can be called without creating objects. Static member functions cannot access non-static members of the class. Static members are useful for class-wide operations and data. Static data members must be defined outside the class, before C++17. Common patterns where static members are used include Singleton, factory, and utility classes. Static members provide a powerful way to share data and functionality across all instances of a class. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.